Okay, so we ended talking about how to organize the electrons around the nucleus of an atom. And now we talked about the quantum mechanical model, and the quantum mechanical model is just a much more complicated model than the Bohr model. Now, I'm still going to use the Bohr model as a reference. Because it's kind of just easier to look at and easier to use. But we do know that instead of these electrons being in these beautiful orbits, right, these rings or these shells around the nucleus, that they actually are in what are called these orbitals, which are regions where you have a good probability of finding them. And the way these were determined was from pretty complicated calculus. But the reason that this had to happen was because electrons are constantly moving, so you can't possibly know where they are and how fast they're moving at the same time because they're constantly moving. So you can only guess a probability of where they could be at any given moment. And so they called these regions orbitals, and they're just more complicated than just like a simple ring, a first ring and a second ring and a third ring. So that's the quantum mechanical model that we're going to use. Now there's all these rules of how you have to fill in electrons around the nucleus. There's the Aufbau rule, the Pauli exclusion principle, and Hund's rule. And so we follow these rules to fill in however many electrons our atomic number says we have, because we're doing all neutral atoms for right now. And you just fill them in around the nucleus, kind of like in this pattern. So now let's refresh. S orbitals. The S orbitals start on the first energy level, and there's one shape. It's a sphere. A sphere is a sphere is a sphere. You can't have any other shapes for a sphere. So that's why when you see all the 1s, 2s, 3s, 4s, 5s, there's only one box. That one box represents one orbital. The s orbital has one orbital or one shape. All right. Now, when you look at all of the p orbitals, look at 2p, 3p, 4p, 5p. So there's three boxes for all of them. That's because there's three orbitals or three shapes. There's px, py, pz for all of them. Px, py, pz, px, py, pz, px, py, pz. So there's three orbitals for the p orbitals. Now they all look like dumbbell, but they're just rotated along different axes. Now your d orbitals, 3D, 4D, 5D, 6D. They all have five boxes. There's five boxes because there are five different orbitals for D, or five different shapes. Four of which kind of look like that four-leaf clover shape, and then the other one kind of looks like a weird thing. It's like a donut with something shoved through the middle of it. Okay. And then your F orbitals, or your F block, okay, there are seven shapes, which is why there are seven boxes, meaning there's seven regions that you could potentially find an electron around the nucleus of an atom. So these are just different orbital notations for second period elements, right? Elements in the second row. And instead of drawing them like going upwards, they just drew them going across. Not a big deal. So look at carbon has 6 electrons. So you put 2 in the first orbital, 2 in the second orbital, and then you spread them out in the third orbital, or in the 2p orbitals, I should say, I guess. You spread them out, right? That's Hund's rule. They don't want to be next to each other because electrons repel other electrons. So they'll spread themselves out. And then you just keep going. You spread them out even more. And then you're forced to pair them up because you can't jump up to a higher energy level first. And then for 9, you got to force another one up. And then look at neon. This is a full orbital, right? We know our noble gases are really stable for this reason because they have a full valence shell. Okay. So when we go to write electron configurations, we always write them in the same exact way. You write what energy level you're on. That means your principal quantum number, n equals 1. This is what row you're on. First row, second row, third row, fourth row on the periodic table. And then you write what block you're in or what orbital you're doing. So like S. And then you include how many electrons. And then you put that up as like an exponent, which is called a superscript. And then you just keep going. It's always the energy level you're on, the orbital you're in, and how many electrons. And then we're going to read the periodic table like a book, okay? And these 3 words I'm going to use very frequently today: highest occupied energy level, valence electrons, and inner shell electrons. And it's going to describe where the electrons are around the nucleus of an atom. So I'm going to do these first 2 with you, Okay, I'll do the first two with you. Actually, I'm gonna do the first three with you. Practice, and hopefully it will help you better understand how to do electron configurations, and then you're gonna try the other three. So we need a periodic table. We're gonna do the electron configuration for lithium. So we're gonna go find lithium on our periodic table, and it is right here. Okay, now remember, this is n equals 1, n equals 2, n equals 3, 4, right? These are just what rows you're on or what shell you're in, okay? So what you have to do is you have to read your periodic table like a book, where hydrogen is the beginning of our book, okay? And you read the periodic table until you get to the element that you want for whatever they're asking for the electron configuration. Now, I'm going to refresh our memory. Your alkali and alkaline earth metals are your S block elements. Your transition metals are your D block elements. And then these guys, oops, this is what I did earlier, are your P block. I want to do different colors. So this is D. Okay. This is S. And then your F block elements are down here. Okay, so you're just going to need to know that. And after we do a bunch of these, you will. Now be very, very careful. Helium is considered an S block element. I realize it is lined up over here, but the only reason that it is lined up over here is because it has a full shell like your noble gases, so it is a noble gas. But it really is an S block element, so don't confuse that, okay? Okay, so having said that, I'm going to erase everything now. And we're going to read the periodic table like a book. So I start on the first energy level, 1. Oh, someone have a question? So Martin asked if the highest energy level was the same as the valence shell. Yes, it is. The valence shell, the outermost shell. So again, hydrogen is 1 on the first row. That's what the 1 means. This is the S block, so I write S. And I count 1, 2, and I put that up here. I have 2 electrons now. I haven't hit lithium yet, so I got to keep going. What row am I on? 2. This is the, right, 1, row 1, row 2, row 3, row 4, blah, blah, blah. Second row, what block is this? S block. Now I'm at lithium. 1. Yes, you have to put the 1. This is the electron configuration for lithium. 1s2, 2s1. So 1s2, 2s1. Okay, let's try oxygen. So now for oxygen, we are going to have to read the book until here, because that's where oxygen is. So again, we always start at the same spot. Hydrogen. Everybody starts there. So what energy level is it on? 1. What block? S. 1, 2. Okay, now I'm at helium. Have I gotten to oxygen yet? No, so I'm not done. So what energy level am I on now? 2. I'm on the second row. What block is this right here? S. How many elements? 2. Now I'm at beryllium. I haven't gotten oxygen yet, so I have to keep reading. Still on the second energy level, right? But this is the P block over here, so I have to write P now. 1, 2, 3, 4. 2p4. So 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. Okay, what about chlorine? So chlorine, find it on our periodic table. Ooh, whoopsies. Okay, it's right here. So I have to read my book or my periodic table till I hit chlorine. So energy level 1, right here. S, and there's 1, 2. Energy level 2. S, oops, sorry, 1, 2. S block, and there's 2. Energy level 2 still, but now this is the P block over here. 1, 2, 3, 4, 5, 6. 6. I'm still not to chlorine, so now I got to keep going. Now I'm on my third energy level. This is the S block. 1, 2. I got to keep reading. This is the third energy level, right? This is the 1, 2, 3, 4, 5. This is the P block. and I had to count over 5. So this is the electron configuration for chlorine. So 1s2, 2s2, 2p6, 3s2, 3p5. Any questions so far? Okay, now before we move on, I want to do a little bit of a refresher. So we had said, right, this is 1s, 2s, 3s, 4s, 5s, right? And then this is 2p, 3p, 4p, 5p, and so forth. I guess I could do them all, 6s, 7s, 6p. Okay, now you have to be careful because I don't know if you remember, but does anybody remember where the d orbitals, right? This is, so after 4s, this is the d block, right? We haven't hit the d block yet. But what do we call these guys? Does anybody remember? 3D. Good job. 3D. I realize they do line up with the 4th row, but they're really on the 3rd energy level. And if you want to think of it this way, they're really on the 3rd ring. These guys are on the 4th ring, and these electrons are on the 3rd ring. So that means the D block is always 1 energy level behind the S block. So if this is 5s, this is 4D. Okay? So if this is 6s, this is 5D. Now, here's what's tricky. When we've been reading the periodic table, we haven't really paid attention to like lanthanides and actinides, and we really haven't worked with a lot of elements so much down here. But if you look at the numbers on the periodic table, it goes 55, 56, 57, right here, and then 58 is down here. So when you're reading, you really go through the F block and then back to the D block, okay? Now, the other tricky part is, does anybody remember where F orbitals begin? What energy level do F orbitals start on? Anybody remember? 4. So the F orbitals are 1 behind the D block. So D is 1 behind the S, and F is 1 behind the D, or you could say F is 2 behind the S in terms of energy levels, which makes, if this row is 4F, this row is 5F. Okay? So the S and the P line up perfectly with the periodic table. They're often referred to as your representative elements. And then your D and F they fall behind in terms of energy levels. Questions so far? So having said that, I want to give you a minute or two to please practice the cobalt and the argon and the tin. So I'll give you a minute or two to see if you can do those on your own. All right, so this is what I have for the cobalt, argon, and tin electron configurations. Are there any questions about these so far before I talk a little bit more about them? Any questions? Okay. So now we need to use some of the vocab terms that I briefly introduced. So we're going to talk about highest occupied energy level, which is often referred to as the valence shell. It's the outermost shell of electrons. And the reason that the valence shell is important is because the valence shell has the electrons that will be involved in bonding and will determine how certain atoms behave chemically. So we're going to do that and the valence electrons. Okay, now before I do any of that, a long time ago, and it would probably happen in biology or maybe another time in your, oops, I'm not going to use this one. I've been having issues with that. Okay. A long time ago, you probably were taught and were just kind of forced to memorize number of valence electrons in each family. So does anybody remember how many valence electrons the alkali metal family plus hydrogen have? How many valence electrons in this first column? One, all right? One. And then your alkaline earth metals were 2. And then the boron family was 3. And the carbon family was 4. And the nitrogen family is 5, 6, 7. And I'm going to put the 8 here because helium technically has 2, but most of your noble gases have 8. And there's a pattern. All right, and you were taught this, and the reason you were taught this, and if you were taught it in bio, you were taught it because you needed to know what charges things wanted to be for ionic compounds. So things that have one valence electron would really like to lose one, and when they do, they become +1. And then when your alkaline earth metals lose them, they become +2. And when your boron family lose them, they become +3. And then the carbon family is strange. It's plus or minus 4. And then once you got to nitrogen, it was actually easier to gain electrons than it was to lose them. So they're 3 away from a noble gas. So they would gain 3 and be -3, -2, -1, and then again, no charge. All right. So the valence electrons helped you identify how to know what the common ion would be for that element in an ionic compound. So now we're going to use electron configuration to prove it. So the first element we did was what? Lithium. Lithium, it's an alkali metal. Based on the cheating way, we remember that alkali metals had one, why is this not going? Had one valence electron. Right? All your alkali metals have one valence electron according to when we kind of taught you that off the bat. So look at, what is the highest occupied energy level? Well, for lithium, that's going to be right here. It's called N equals 2. Energy level 2, aka the second row, aka the second ring. How many electrons are in there? Oh, 1. That's where it comes from, that one valence electron. So these electrons right here are considered inner shell electrons. This is my valence shell, and these are my inner shell. Questions on those 2 words? We're going to practice with all of these. So for oxygen, what is the highest occupied energy level for oxygen? N equals what? 2, right? The second ring, N equals 2. If you want to think of it in terms of the Bohr model, these electrons in here are all in the second ring. That's your valence shell, your highest occupied energy level. So, how many valence electrons does oxygen have? Well, 2 right here, plus 4 more right here, is 6. 6 valence electrons. Okay, chlorine. What's the highest occupied energy level for chlorine? N equals what? Anybody?
3.
3. Your third energy level, which in the Bohr model would be the third ring. Okay, so N equals 3. So how many valence electrons are in there? 2 plus 5 is 7. We know all of our halogens have 7 valence electrons. Now you got to be careful with transition metals, which I don't know if you noticed, but when we're looking at the periodic table, we've kind of completely ignored any patterns within the transition metal block. Okay, there's a reason. It's because they don't follow a pattern. We usually just use the S and the P block, which are referred to as your representative elements. So, what is the highest occupied energy level for cobalt? 4. So when you think of this, you have to think of this as your 4th ring. These electrons right here are on your 3rd ring. So this is your valence shell. So N equals 4. That's the highest occupied energy level. So how many valence electrons does cobalt have in its valence shell? 2. Okay, these 2. These are inner shell electrons. Okay. Okay, what about argon? We know all of our noble gases have how many valence electrons? You learned it a long time ago. What's the magic number for noble gases besides helium? It's 8, right? An octet, that's like that fancy word. Well, let's look at it. The highest occupied energy level for argon is N equals 3. How many valence electrons? Well, there's 2 here and there's 6 here. That's 8. Okay. Now, before I even go to the periodic table, maybe you can. What family is tin a part of? Who is tin in the same family with? It is a nonmetal, yes. Well, tin is not a nonmetal, but it is in a family with some nonmetals. But like who? What elements?
Carbon.
Carbon's 1. Silicon's another, right? How many valence electrons do we know carbon has? 4, right? The whole carbon family has 4. So let's see. Tin, highest occupied energy level is the 5th. So that means this guy and this guy. These are both on the 5th ring, if you want to think about it that way. So the 5th energy level, 2 electrons here, 2 more here, so N equals 5. That's 4 valence electrons, which makes sense because tin lines up with the carbon family, which has 4 valence electrons. Any questions before I move on so far? All right. So there are some exceptions, and the exceptions do not follow the off-bow principle. Okay, which is the order of filling. So before I get to the chromium family are your exceptions and the copper family, which I'll talk about in a minute. But before I do that, please now, I don't want you to do the exceptions. I want you to do based on how you know how to write electron configurations. Please write the electron configuration for chromium your way, the way we've been learning, and please write it for copper, the way we've been learning. I'll give you a minute. Okay, so based on the rules that we know, this should be what you have put based on what we've learned so far. Do you have any questions just based on normal electron configuration? So the exceptions, there's 6 of them. It's the chromium family on the periodic table and the copper family. The copper family is often referred to as noble metals. Noble meaning they're generally stable, right? This is what you see like lots of jewelry and things like copper wiring made out of. Obviously, if they're noble and they're stable, right, if they're going to make jewelry out of them, that would make sense. You don't want some sort of metal they're making jewelry out of that it like rains and you got this like, beautiful gold bracelet on and then it rains and it like blows up on your wrist. That would kind of be problematic, right? So these noble metals tend to be really, really, really unreactive and stable. And then the chromium family, again, let me reference back to the periodic table. So these guys and these guys, these are your 6. We're not going to pay attention to radioactive elements. They don't, whatever. They're man-made and they're radioactive and we're not going to pay attention to them. So these 3 and these 3, that's a total of 6. So here's what happens. This configuration is actually slightly less stable. So I'm going to fill in my electrons into these orbitals. So 1, 2, 1, 2, 3, 4. Okay, and then 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now these, the s, the 4s, and the 3d orbitals are actually very similar in energy. And because they're similar in energy, electrons can move pretty easily between the two types of orbitals. Now, what's interesting is that we've discovered that half-full orbitals tend to have similar stability as full shells of orbitals. So, right, we know all of our noble gases are really, really stable, and the reason they're really stable is because they have full shells of electrons. So what happens is this electron right here actually jumps to this empty d orbital. Now you have minimized repulsion between the two electrons in the s orbital, and you've created a half-full shell. This is a half-full d orbital. It has 5 out of the max 10 electrons. And then, I know this is hard to see, so I'll kind of like redraw this. There's an electron in here, right? This is now a half-full s orbital, half-full, right? S orbitals max out at 2 electrons. So you have 2 half-full shells, and half-full is very, very similar in stability to full orbitals. So the reason it does this is to achieve a more stable configuration. That's all elements in atoms want to do. They either lose electrons, gain electrons, share electrons, move electrons around in order to be stable. That's the whole point, is to achieve stability. So 4s1, 3d 1, 2, 3, 4, 5. It's an exception to our off-bow rule. Our off-bow rule says you'll fill in the lower energy orbital first and then jump up. Well, this one defies that. One of these actually goes into the d orbital to keep repulsion down in the s orbital and create half-full shells. So now molybdenum and tungsten also do that same exact thing in the chromium family. So what do you suspect, having taught you this now, that the copper family electrons do? So the copper family has a different amount of electrons. The copper ends up with 4s2, 3d9. Now notice when I did this, I chopped off these electrons over here. Okay, these are like your inner shell electrons. And yes, while I understand that this is inner shell electrons, they still are a little slightly elevated in energy, so I include them at the end, or in my diagram. I didn't include any of my inner shell because they're not relevant in terms of these exceptions. Okay, so here's 4s2, here's 3d9. Any suggestions of what might happen knowing what I just taught you about the chromium family? Well, one of these s electrons is going to now fill the shell. So now I have a full shell for 3D, and I have a half full shell for the S, the 4S. This is more stable than it being the original way we had it. So it is not 4s2 3d9, it is 4s1 3d10. I've created a full shell and a half full shell. This is more stable. A full shell is very stable, and I've also minimized repulsion between the two electrons in the s orbital. And so silver and gold also do this. These are exceptions. Any questions before I move on? Okay. So this slide explains everything I just did. All right. And now we are going to get to the fun, nice, shortcut, easy part, which is known as noble gas notation, sometimes referred to as core notation. So what I need you to do is, so we've done orbital notation, that's where you put them in the boxes or the circles. We've done electron configuration, where you just read the periodic table and fill in the electrons that way, according to the order that the periodic table goes in. And then now we're going to do what's considered the shortcut way, noble gas notation or core notation, because it's really helpful when you have atoms that have, like, I don't know, 80 electrons, instead of being like 1s2, 2s2. Ugh, it would be like a really long one, right? This will help us do that in a more simplified manner. So before I do it, I would like you to write the electron configuration for magnesium, and then again, please write the electron configuration for neon. I hate when that happens. All right, so here's the electron configuration for magnesium, and here's the electron configuration for neon. If you notice, the electron configuration up to here is identical to the electron configuration for neon. Now, neon being a noble gas. So I had a great question last period. It says, why can't I use any other element? Well, because this is called noble gas notation, so you must use a noble gas for this. So what that means is, for noble gas notation, and it's often referred to as like a shortcut method, is for this first whole part, I'm going to account for all of the electrons up until the noble gas neon. So if you were to look on your periodic table, okay, and you find magnesium, the noble gas that comes before magnesium is neon. You cannot use the noble gas that comes after. It has too many electrons, okay? So the noble gas that comes before magnesium, oops, sorry, I keep doing this, is neon. So you put it in brackets. Oops, I keep going backwards, I'm sorry. And what you're saying is, I'm accounting for this entire part right here. So I'm not going to write any of that out. All I'm going to do is write out what's left over, which is 3s2. I want to put my neon in purple. Okay, and this is called noble gas notation. So these are all like inner shell electrons, and you just put them in brackets, which means you don't have to write any of that. And then what's left over? 3s2. So look at, what's the highest occupied energy level? It's the third. This is like easier to see, right? It's the third, right? Third energy level. How many valence electrons? 2. That should make sense. Magnesium is an alkaline earth metal, so it has 2 valence electrons. Okay, and again, you'll always use the noble gas that comes before the element you're trying to write the configuration for. So again, they sometimes call this core notation because these guys are considered core or inner shell electrons. So I'm going to do practice with you. We're going to do the first, or I'm going to do calcium and carbon with you, and then I'm going to let you try to do the other ones. So I'm going to do carbon first. So you go to your periodic table. You go find carbon. It's right here. And you go, okay, who is the noble gas that comes before carbon? So you go backwards, and it's helium. And you put it in brackets. So you write He. That means I've accounted for all of the electrons up until helium. Okay, so now you write what's left over. Well, I'm on my second energy level, right? This is energy level 2. This is the S block, 2 electrons. Keep going. Second energy level, this is the P block, 2 electrons. And now I'm at carbon. This is the noble gas notation for carbon. Okay, now we're going to do calcium. So you go on your periodic table and you find calcium. It is here. Actually, I'm going to clean all this off. Here. Well, now what's really nice is you're going to find the noble gas that comes before calcium. Well, who's the noble gas that comes before calcium? Argon. And you put it in brackets. Now, what that means is if you've accounted for all of the electrons, all of these inner shell core electrons up until argon. And now all you have to do is write what's left over. So now I'm on what energy level? 1, 2, 3, 4. I'm in my S block. 1, 2. This is, right? This is like easy. It's a lot less work. Noble gas notation is a lot less work. And on a test or, whatever, it'll say write in noble gas notation. If it doesn't, you're not allowed to write it like this. Okay, again, this is a shortcut. So you would see how this would be nice if I had you do like bismuth. 83 electrons, oh my gosh. It's not that it would be hard per se, it's just kind of tedious and it would take a while. So noble gas notation helps us especially with really, with atoms that have a large number of electrons. So this is calcium's noble gas notation. So I would like you to please try the rest on your own, and then we will go over them. Remember that copper is one of our exceptions to the Aufbau principle. Oh, Kieran, were you asking what I was doing like for my PowerPoint or for my slides, what I was trying to fix? I'm constantly trying to make my slides better and better formatted. So I was trying to, for the other slide, I'm going to put all of them in boxes or in like a table, and then like have the highest occupied energy level column and valence electrons for all of them instead of having to erase and rewrite. I figure it would look neater. I'm always trying to improve. Okay, are there any questions on these noble gas notations? I do want to talk about gallium for a second. Only because sometimes when there's the 3D block in there, it throws kids off for like when I say, hey, highest occupied energy level for gallium. What is it?
3.
3. Ooh.
Oh no, 4.
Thank you, 4. That's okay. So 4, right? So how many valence electrons? Be very careful. Kids will just go, oh, 1. No, 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 no. This is on the 4th ring, and this is on the 4th ring, if you want to think about it in terms of the Bohr model. So 3 valence electrons. Let's find it on the periodic table. Look at gallium. This is the 3 valence electron family, right? 1, 2, 3. Okay. So I want to talk to you about something that you kind of, again, were taught a long time ago that may not have made sense. And I'm going to go here. All right. Remember the Bohr model of the atom, right? Where you have one ring, and then you have a second ring, and then you have a third ring. And then I'm just only going to draw 4, but there's more, right? There's 7 rings for the periodic table for the sake of our periodic table right now. So, right, this is n equals 1. This is n equals 2, n equals 3, n equals 4. All right. So if you remember way, way back, and this, maybe you learned this and maybe you didn't. Oh, dang it. I've been trying to do stuff color coordinated and my OCD is now kicking in. Do you remember when they taught you this way back in the day when you tried to when you had to fill in electrons? Do you remember how many they let you fill in on the first ring? And again, I kind of already cheated and taught you this, but do you remember how many electrons were allowed on the first ring? 2. Beautiful. Okay. Let's talk about why. So I'm going to tie some concepts in together. So 2, I'm going to draw my 2 electrons. These are these lines, right? Maximum of 2 electrons. Well, why is that? Which orbitals are present on the first energy level? Are there s orbitals on the first energy level? First energy level means first row, right? Right here, first energy level. Are there s orbitals? Yes, right? There's s orbitals. Are there p orbitals? Is there such thing called 1p? Is there such thing called 1p? Have you ever heard of anything called 1p?
No.
No. So if there's only s orbitals on the first energy level and s orbitals, there's only one shape, right? You max out at 2 electrons. That's why you're only allowed to throw 2 electrons in there. Now, what about n equals 2? So back in the day, they told you got to throw how many electrons in your second ring? 8, right? That's what you learned. So 1, 2, 3, 4, 5, 6, 7, 8. So let's talk about why. Well, what orbitals are on the second energy level? Are there s orbitals? Yes. There's s orbitals on every energy level. And those can max out at 2, right? What other orbitals are on the second energy level? The p orbitals. So look at, if we go back to our periodic table, you've got your p orbitals, right? This is p, 1, 2, 3, 4, 5, 6. That's how many electrons the p orbitals can hold. And you go, oh, so there are p orbitals. Oh, no, stop that. Sorry. Oh my gosh, what's happening? Okay, so there are p orbitals here present. Whoa, that's not a p. And our p orbitals can hold 6 electrons. There's 3 shapes. 2 can go in each shape, or 3 orbitals. Px, Py, Pz, Pz. And you can throw 2 in each of these, so that's why you max out at 6. Well, what does that add up to? That adds up to 8 electrons in your second shell, or second ring. Now, you might not have learned this, so I'm going to teach it to you now. The D, sorry, no, I just killed it. So the third energy level, we have s orbitals, which can hold a maximum of 2. Let's look at our periodic table. Where's my s orbitals? Right here, right? Two, 2, 2, 2, 2, right? So those can hold 2. We have p orbitals, right? There's 3p. Go back to your periodic table. The third row, there's a p block. It's right here. Okay, those can hold 6 maximum electrons. Now, you look at your periodic table and you go, oh, the third row, that's all there is, S and P. Is that actually true, though? On the third energy level, is what orbitals begin on the third energy level? What are these guys called? 3D, right? I realize that they don't line up well with your periodic table, but there is such thing as 3D. Your d orbitals are present on the third energy level. Now, how many electrons can your d orbitals hold? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many electrons can you throw on that third ring? 2 plus 6 is 8 plus 10 is 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's where you max out. So n equals 4. Sorry, I kind of ran out of room. So you have s orbitals for sure. 4s2, right? And those can hold 2 electrons. There's p orbitals, 4p. And those can hold 6 electrons. There is such thing as 4d, and those can hold 10 electrons. Anything else on your fourth energy level? What's this guy called? 4f. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 7 orbitals, 7 types of f orbitals, and they max out at 2 each orbital. So that's 14 electrons that I can account for from the F, which means your 4th energy level on can hold, what's this? 14 plus 6, or I'm sorry, 24 plus 6 is 30 plus 2 is 32 electrons. Oops, I forgot to do the. I'm hoping this is kind of tying up some loose ends where, right, the p orbitals have 3 shapes, right? 1, 2, 3. 2 in each orbital, that's 6 electrons. If you count across the p block, there are 6 elements in every single period on the p block. Okay, so this, again, I know the Bohr model is a lot more simplistic compared to the quantum mechanical model, but this is a general idea of how many electrons you can put in each energy level based on orbitals. 32 would be for 4 and 5, and then that's only because we don't have elements past the 5th 5F. But really what happens is they can be empty, which means you could put more in if you wanted to. So yes, we don't have them filled in, but they can still be empty to put extra electrons into. Does that make sense? So yes, we don't have elements that fill beyond the 5F. I mean, they can fill 5F to 7P. So there's no such thing as 6F in terms of an element that has an electrons for that. But potentially there could be empty orbitals that exist for those. Okay. Again, we won't even go beyond that. So now that I have done that, let's talk about ions. For ion configuration, it is not too bad. All you have to do is add or remove electrons based on who the ion is. So let's practice. All I want you to do right now, and I know I only have 7 minutes, but I still should finish this slide. I want you to take a moment and write out all of the normal neutral electron configurations. So write iron, fluorine, aluminum, copper, calcium. I don't need you to mess with electrons yet. Just write them normal. So go write the normal electron configuration for neutral iron. And so here we go. So these are our normal neutral ground state, as we would call it, electron configurations. They're called ground state because they're just like normal. Nothing fun or exciting has happened. So +2. We're always going to remove from the valence shell first. So you look at the valence shell is your highest occupied energy level. That is 4. 4 is the highest occupied energy level. It's the 4th shell or the 4th ring. +2 means I remove 2. Sweet, there's 2 in there. See ya. Here's the electron configuration for iron +2. Now notice, remember, transition metals are often, they often have different oxidation states, right? They like to do B+2, or sometimes they can be +3. So here is iron +2. Now let's look at what iron +3 would be. So you need to remove 2 electrons from the valence shell first, right? This is my valence shell. So all 2 of those are gone. But I have to remove a 3rd electron. Now, you will remove from the d orbital next. The reason that is this 3d orbital is slightly shielded by the 3s and the 3p orbitals, making the electron easier to remove from there. So you would remove from the d orbital next. And so this is the electron configuration for the iron ion 3+. Okay, how about F-? Well, I'm going to just draw the orbitals. I know the bell will ring. Please just bear with me. I know you can. Please, please, please. So this is, oops, this is 2s right here, orbitals. This is 2p, okay? And it looks like this. Neutral. And then it's going to gain 1, right? So look at, there's an empty spot for it. There it is. So it will go in, this is the s orbital is full. You max out at 2 in the s orbital. You don't max out till 6 in the p orbital, so that's where the extra electron goes. Look at this is isoelectronic with neon, right? Okay, so aluminum +3 means I have to get rid of 3 electrons. You find your highest occupied energy level. It is right here, the third shell. There are perfectly 2 plus 1 is 3. So I'm going to lose that entire third shell of electrons. Now, I also have the same exact configuration as the fluoride ion. That means aluminum ion and fluoride ion are isoelectronic with one another. They have the same number of electrons. What about copper +1? Well, +1 means I have to lose 1 electron. Again, you lose from the valence shell. The fourth ring, or the fourth shell, is the valence shell, and there's 1 electron conveniently in there. Remember, copper is an exception. And so that thing goes bye-bye. And then this is what you're left with. Oops, sorry, I accidentally erased this. This should be 3p6. Okay? Calcium +2. I got to lose 2 electrons. I'm always going to lose from my valence shell first. There's conveniently 2 electrons in there. So this is the electron configuration for the ion of calcium.